In our last explainer, we got into the weeds with the tricky math of floating point numbers. Well, today, we're going to go a level deeper. We're going to demystify how modern game engines pull off their breathtaking speed. And to do that, we have to understand the actual architecture of the chips they run on.
You know, we often think of code as this abstract thing, kind of like a ghost in the machine. But it's not. It's real. It's electricity, physically moving through silicon. So if you really want to understand how games hit that silky smooth 60 frames per second, you got to stop thinking about abstract code and start visualizing the CPU as a physical workspace, a bustling factory with its own geography, its own highways, and its own very real speed limits. All right, so here's our game plan. We'll kick things off with the one big problem every game developer has to solve. Then, we'll look at the old, painfully slow way of doing things before we get to the revolution that changed everything. After that, we'll take a tour of the hardware itself, and finally, spill the secrets that engineers use to squeeze every last drop of performance out of the machine. At the very heart of all modern game design, there is a single, brutal, unyielding constraint. It's a frantic race against a clock that resets itself 60 times every single second. That's it, 16 milliseconds, just 16 thousandths of a second. That is the entire time budget a game gets to do everything. I'm talking calculating physics, processing your button presses, figuring out what all the bad guys are going to do, and drawing the entire world onto your screen. If the game takes even a fraction of a millisecond too long, the whole illusion of a smooth, believable world just shatters. I mean, just picture the absolute chaos of a modern game scene. Every single bullet has a position, a velocity, a trajectory. Every little piece of debris from an explosion has mass and is being pulled on by gravity. All of it is just one massive, complex math problem. And just like this little CPU guy knows, that hourglass is always running out. It's this relentless pressure that forces engineers to find much, much smarter ways to get the math done. So what makes this so incredibly hard? Well, for a very long time, computers worked in a very linear, one-track kind of way. And that created the fundamental bottleneck that absolutely had to be overcome. This old method is called scalar processing, and the best way to think about it is like a single-lane toll booth. Let's say you have 4 bullets whose physics you need to update. The CPU processes bullet 1, then it processes bullet 2, then 3, then 4, one at a time. Now, instead of 4 bullets, imagine 10,000 pieces of debris from an explosion. This one-at-a-time method is an absolute guarantee for lag. It just can't keep up. But what if we could just upgrade the road? This brings us to the real hero of our story today. It's a kind of cheat code built right into the hardware itself that makes all of modern gaming even possible. It's called SIMD, which stands for Single Instruction Multiple Data. And honestly, it does exactly what it says on the tin. With just one command, you can perform the exact same operation on a whole bunch of data at once. So instead of telling the CPU, add this one number, you get to say add all of these numbers. And it just does it all in one go. So what we do is we tear down that sad single-lane toll booth and we build this, a 4-lane superhighway. Now 4 cars, or 4 pieces of our data, can roll up at the exact same time. The toll booth operator hits one single button and bam, all 4 gates swing open in the same nanosecond. All 4 calculations happen for the price of 1. You've instantly quadrupled your throughput. It's a total revolution in efficiency. Okay, so that's the big idea. It sounds great in theory, but how does this actually work down in the physical silicon? To see that, we need to take a little tour of the CPU itself and see how it's really built. A CPU's power is basically defined by its word size. That's just a fancy way of saying how much data it can grab and work on at once. Way back in the late 70s, a 16-bit register was like a tiny teacup. It could hold one small number. That grew to a 32-bit bucket, then a 64-bit suitcase. But modern SIMD registers, well, they are something else entirely. These huge 128-bit registers, they're called XMM registers, are best imagined as cafeteria trays. And here's why that metaphor works so perfectly. A standard floating point number, like we talked about last time, is 32 bits wide. Well, a 128-bit tray has exactly enough room for 4 of those. It's like it has 4 compartments, or lanes. So you can load 4 separate numbers onto this tray, and then a single command, like add PS, which literally just means add packed single precision floats, tells the CPU to do the math on all 4 lanes at the exact same time. Now, this is absolutely crucial to understand. The CPU isn't just one big uniform block. It's physically divided.
You've got the vector island. Think of that as the factory floor, where all the heavy-duty SIMD math is happening, on those big cafeteria trays. And then you have the integer island. That's more like the manager's cabin, where all the logic and the if-else decisions are handled by smaller, general-purpose registers. And believe me, the physical distance between those two islands really matters.
Because once you understand this geography, you can finally understand the really clever, advanced tricks that engineers use to push performance to its absolute limit. These are the real secrets of optimization.
Okay, so if you're a programmer, you're taught to write nice, clean code broken up into small, readable functions. It's good practice. But for the CPU, our little office clerk, it's a bureaucratic nightmare. To run one of those functions, our clerk has to stop what he's doing, bookmark his page, pack up all the data he needs, and then take a long, slow elevator ride to a completely different memory address. The actual math might take a single nanosecond, but the commute can take 10 times that. This is what we call function call overhead.
This is where the compiler steps in, and it acts like a ruthless, super efficient office manager. It sees our clerk planning this whole expensive trip just to do a simple 2 plus 2 calculation. The manager just vetoes the trip, boards up the elevator, and copy-pastes the instructions from that other floor right onto the clerk's desk. This trick is called inlining, and it's a perfect example of a zero-cost abstraction. The programmer gets to write clean, organized code, but the machine gets raw, uninterrupted speed. The middleman completely disappears.
So, remember our two islands? Well, moving data between them is incredibly expensive. Let's say you need to take just one number from the math factory over to the manager's cabin to make a decision. That data has to cross a physical bridge on the chip, and that trip can take anywhere from 5 to 20 CPU cycles. And while that data is in transit, the entire factory assembly line, the pipeline, it just grinds to a halt. Everybody just stands around, waiting. It's a disaster.
So the number one rule of optimization becomes stay on the factory floor for as long as you possibly can. And there's a clever trick for this called splatting. Let's say a calculation gives you a single number, like 5.0. Instead of sending that one number on a long trip across the bridge, you just broadcast it, or splat it, across all 4 lanes of a brand new cafeteria tray. Yeah, it feels a little redundant, but you save all that costly travel time, and most importantly, you keep the assembly line moving.
But the ultimate trick is to avoid those trips to the manager's cabin altogether. An if-else statement is what we call a branch. It's a fork in the road. The CPU has to guess which path the code is going to take, and if it guesses wrong, it has to backtrack and redo the work, wasting precious time. Branchless logic avoids this whole guessing game. Using a special instruction, we can turn a logic question, like, hey, which of these 4 objects just collided, into a simple mathematical bit pattern. A 1 means yes, it hit. A 0 means no, it didn't. So you just get a result like 1001. The processing flow stays perfectly straight and predictable. You've turned a risky guess into a simple mathematical guarantee.
So you might be wondering, why not just use massive 512-bit registers for everything? I mean, why stop at 4 lanes? Well, because there's a final boss in this game, and its name is thermodynamics. Moving that much electricity around generates an incredible amount of heat, and that forces the CPU to slow itself down, or throttle, to keep from literally melting. So the true art of optimization is this delicate, constant balancing act between the width of your highway, the speed of your cars, and the heat that they generate. So, the next time you're deep in a game and you hear your computer's fan spin up and start to roar, just remember, you're not just hearing a fan, you're hearing the sound of friction. You're hearing the sound of millions and millions of those cafeteria trays being loaded, processed, and emptied every single nanosecond. That is the true sound of the architecture of speed. In the next video, we'll explore assembly-level optimization.